All right, welcome back, everybody. In this lecture, as mentioned in the previous one, we're going to be transitioning from biological psychology to a new branch of psychology called cognitive psychology. There's lots of different things that we can cover in this branch of psychology. We can spend our times talking about attention and thinking and problem solving, something we will actually be discussing later on. But if we're going to try to narrow down the scope of what cognitive psychologists study, how they focus on not necessarily individual differences, but basic principles of how the mind works. We usually, in an intro class, start out by talking about the process that very closely ties to biological psychology topics, one that's called perception. Obviously, in our last class, we spent a lot of time talking about sensation and the structure of the eye and how it allowed us to convert those energies in from the environment that we call electromagnetic energies into some type of neural signal that our brain can then break down into something that we can eventually make sense of. Well, if you remember back to the end of that previous lecture, I remember me spending a lot of time talking about all the different things that happened along the way. So some type of signal got to the brain, and then we spent a little bit of time talking about how the different paths within the brain had an impact on different elements of vision that we were processing. Well, as a reminder, this specific type of sense, vision, is just one of many senses, and when we're talking about perception, well, we can talk about, if you take a sensation and perception class, numerous different sensations and perceptions that are going on at any given point in time. But since we've already spent a lot of time talking about visual sensation, we're going to be dedicating this class to visual perception. Just want you to bear in mind that, again, visual perception is not the only thing that cognitive psychologists look at. They look at other senses, and they look at other basic mental principles, some of which we'll be covering in future classes, but many of which we just don't have time to cover in an intro class. Now, to start us off with this discussion on visual perception, what I'd like to do is an activity that sort of replicates what we would do in an in-person class. If this was a traditional in-person class, I would have everybody pair up with other individuals, sit next to each other, and I would tell them I'm about to flash a picture on the screen for just a fraction of a second. I'll be up there for maybe 2 seconds max. But within that 2 seconds, I want you to all get the gist of what's in there and try to talk with the person sitting next to you about what you saw to see if we can not only recognize that all of us saw pretty much the same thing, but all of us caught some of the key elements to the image. Again, this is not an in-person class. If you're visually impaired, obviously this is going to not be something that's really possible, but for those of you that can do this, just so you could get a feel of how challenging this task is, be ready, because on the next slide you're going to see an image. If you've got your notes in front of you, well, you kind of already have seen the image, but just again, so we can replicate what would happen in class, I'm going to flash an image on the screen for 2 seconds, and I'm going to pause afterward to see what it is that you could potentially remember from that image. You won't be able to talk with somebody about it really, but hopefully you'll be able to tick through some of the items in your mind. So here we go in 3, 2, 1. All right. I'll pause here, or if you can, pause me. Just think about some things that you saw. I'm guessing you can pick up on a theme, maybe identify some of the things that were within that image. You could probably actually rattle off 5 to 10 things that you clearly remember just by looking at that for just a fraction of a second. And this is what we're going to focus on first when it comes to visual perception. The fact that you could make sense of so many stimuli hitting your eyes. There was a lot of information there in that image, but I'm guessing that most of you, within the 2 seconds that you saw that, were able to get the gist of the image, were able to pick up on, again, 5 to 10 things, and if we were sitting next to somebody, you would find almost 100% agreement from person to person as to what we all saw. That is pretty amazing, right? And this is really speaking to how robust our perceptual skills are. We're able to take all of that information coming from our eyes to our brains, and within a fraction of a second, start to make sense of a large number of things within it. How we do that is what we're going to be focusing on in this class. And when we talk about how we do this, it's probably important to start with a debate that was raging in cognitive psychology for many decades as the field was starting to form. As perceptual psychologists or people studying basic cognitive processes started to identify the multitude of different things that we had to break down whenever we were seeing something. And this goes for every sense. There's a large number of things that we're breaking down in any given moment for all of our senses. They were amazed as to not only how quickly we could do this, but perplexed as to how we went about doing it. In particular, people started to try to figure out if every perceptual experience was a byproduct of just our brain breaking down the environment, or a byproduct of our brain placing expectations on what it was we were going to see or hear or smell or experience. It was really shifting or shaping what it was that we encountered in a given moment. In particular, there was this debate between what was called the constructivist and the ecological approach. Constructivists argued that essentially everything we encounter in any of our senses is experienced not just on its own, but through the interplay between what we anticipate seeing, what we've kind of learned to expect to see in certain situations, and what's actually there. We nowadays call a lot of the things that they looked at top-down processing, even though for constructivists at the time, when they originally proposed this idea, it was less about the input the brain had and more about this notion that the brain, the mind, was the driving force behind our perceptual experiences. The people in opposition to the constructivists in the early years were these individuals who used what was called the ecological approach to perception. They surmised that pretty much everything we experience through our perceptual, orifices were really, or actually was really, a byproduct of just the elements of the stimuli being processed by those organs. Vision was not our mind placing expectations on things. It was just a breakdown of the signals coming from the eyes in a multitude of different ways. Nowadays, we tend to tie this ecological approach to something called bottom-up processing, but much like top-down processing, it's not necessarily perfectly reflective of the approach that it's linked to. Bottom-up processing is about us trying to make sense of something by using the basic elements of those stimuli to better understand it. It's not necessarily nestled in this notion that that's the only thing we do. But let's continue with this topic of basic visual perception by just contrasting how these two approaches might work and the conversation that unfolded as psychologists were trying to understand something as simple as visual perception. Well, simple is probably not the right term, but something as, well, basic in terms of the large scale of all the things that we're perceiving as visual perception. In particular, we're going to focus our attention in this lecture on what we call color vision, a topic that was very intriguing to a lot of early psychologists because they thought there might be some way, if we did our best, to break down and get a definitive answer as to how color was actually perceived by our minds. And if we want to understand this color vision debate, we have to actually look at several theories, several ideas that were used in an attempt to explain how color vision worked. And the first theory we're going to look at is one of the first theories that was introduced by scientists long before we were able to actually find real proof of whether or not this theory made logical sense. It's a theory that we call the Young-Helmholtz trichromatic theory of color, named essentially after the two individuals that championed this idea. Young and Helmholtz surmised that in our eyes, this is long before we were actually able to verify this, we might have three different types of cells that should potentially be responsive to 3 different types of wavelengths. Now, some of you might be wondering how they could come to that idea. To understand that our understanding of light and how it could be refracted was far ahead of our understanding of biology and the human eye, simply because we had the tools to look at that concept long before we could look at the eye. So Young and Helmholtz, looking at how light worked and doing some basic math computations, said, well, maybe in our eyes we've got these cells that are looking for short wavelength light. The ones where the electromagnetic energy, again, is coming in very fast succession, so the distances between the wavelengths, or the pulses of electromagnetic energy, is relatively small. We might also have these cells in our eyes that are responsive to medium wavelength light, and others that are responsive to what we again call long wavelength light, or the ones that are coming at a relatively slow pace. The distances between them, in terms of nanometers, is significantly larger. They said if we had cells that were responsive to these things, we wouldn't just see these 3 types of colors. Instead, we'd be able to see the whole visual light spectrum, because it would allow us to just kind of do some quick computations in our minds to figure out where the wavelengths of light were based on how responsive these 3 types of cell were to the different types of light present in different spots in our eyes. So if we say we're looking at a purple, we might have our short wavelength lights going nuts, our medium wavelength lights making some noise, and our long wavelength cells being very dormant. As we creep our way up into, say, the yellows, we might have our medium and our long wavelength cells getting extremely active, almost at the same amount, and our short wavelength cells being relatively dormant. And our brain would quickly make that calculation that we're looking at yellow. Of course, this was merely a theory that Young and Helmholtz had, so what they started to do was look for proof. And we couldn't find the cells in the eyes necessarily at this time that could give us proof positive that this worked, so they looked in other places. One of the places they looked was just how people's visual perceptions worked from person to person. What we recognized pretty quickly when trying to understand color perception was that even though the vast majority of the population did see the visible light spectrum in relatively the same way, there did seem to be a small percentage of the population that seemed to miss certain elements of light. This led some researchers to call most individuals who see the visible light spectrum trichromats, and it led others to suggest that there could potentially be some that fit into one of 3 groups. I guess technically there's a 4th group, but primarily one of 3 groups where these people could not see the visible light spectrum. They started to describe these visual deficiencies or visual insensitivities, depending upon the person, deuteranopia, protanopia, and tritanopia. If you look on the right side of this slide, you actually see 3 pairs of lines. For us, we see the line on the top for the deuteranopia pair is very different from the line right below it. But from somebody who does struggle with this color vision deficiency, they can't tell that there's a difference between those 2 lines. Same thing for the protanopia pair and the tritanopia pair. Now, these particular types of color deficiencies are very rare, where we're talking about less than 2 or 3% of the population, and in some cases even less than that, depending upon which populations we're looking at. Instead, what we tend to see more often are these things called color insensitivities, where there's different types of combinations of individuals that can't see certain colors when there aren't clear defined boundaries or transitions, which makes some people not be able to see the numbers 29 and 56 and 8 and 6 and 25 that you see pictured in front of you. And if we break these missing issues down, or these color deficiency or color insensitivity issues down, what we see is very concrete proof that color perception might come from the cells, the 3 types of cells that are responding. Some of you might be asking, what's that 4th type of issue that I mentioned just briefly earlier? It's something that we call monochromatism, where people actually can't see any visible light spectrum, and it's usually paired with people struggling with multiple cones or multiple cells that aren't responding. And kind of just actually gave away a little tidbit about this specific problem. That tidbit being that eventually, when we were able to dissect the eyes, we were able to actually verify that we do indeed have three types of cones that are responsive to the three different types of wavelengths that you see pictured here. And this seems to be very strong evidence for that ecological view or bottom-up view that we talked about before, at least in terms of color vision. Maybe we do just see color as a byproduct of the responses of our cones sending messages into our brains at different amplitudes or different frequencies, and those things could potentially be all we need to understand color. Of course, as I mentioned before, we're just going to look at one theory. We're going to look at other theories as well. And that's because this young Helmholtz trichromatic theory of color vision ran into a bit of an issue as scientists started to pick at it a little bit further. And this issue is actually something that we can replicate here in this class. If you've got color vision issues, or if you have vision issues in general, I apologize, but for those of you that can see things, at least in the typical way, what I'd like for you to do is stare at that flag that you see in the lower right-hand corner of this slide, but not just keep browsing it. Instead, focus your attention on the center X or plus sign in the middle of the flag. And for this effect to work, as I'm talking here for the next minute or so, I need you to not move your eyes. You can blink, but do not move your eyes. Keep your attention fixated on that plus sign. And we can do that as I start to talk about this specific problem, and we're going to see a really interesting effect pretty soon. So while you're focusing on that slide, if the trichromatic theory is all we need to understand color vision, one would surmise that you have all of these different cones sending different messages to the brain so you can know, don't move your eyes when I say these things, but it's sending messages to your brain to let you know that you're seeing lots of green stripes in different areas of your visual field. You're seeing lots of yellow patterns that surround these black stars in another portion of your visual field. Again, don't move your eyes if you want this to work. You get all these messages being screamed at, well, screaming things at your brain, telling you the exact colors you're seeing as a direct byproduct of the cones that we have. If you look at a bright room, you would just assume that your eyes are screaming, I see all these bright colors, I see all these bright colors, or if you're in a dim room, you see all the dim colors. But even though we get these messages constantly bombarding our brain, it doesn't mean that if we say take them away, things stay the same. Like say, for instance, if I remove that flag. Now for those of you that did stare at the screen for long enough, you might be seeing something very peculiar in that lower right-hand corner right now. You might be seeing, instead of the green, yellow, and black flag, a red, white, and blue flag. And you might be wondering, as you're looking at that, still lingering there, how this is possible. Well, this is something we call the afterimage effect. It's very similar to the light and dark contrast that we run into when we're, say, looking at something in a bright room, and then we go into a dim room and start to perceive colors slightly differently. All of these afterimage effects and brightness-darkness contrasts that we have when we've sort of fatigued the signal going to the brain and caused things to sort of be recalibrated can't be explained very well through just the trichromatic theory. So theorists scrambled to try to figure out a solution for these effects that we were discovering many years after the trichromatic theory was introduced. One of the ideas that started to really be pushed was this concept of something called the opponent process theory of color vision. It suggested that maybe in addition to signals coming from cones, we had extra signals coming from other cells, potentially in our eyes, that were telling us about contrasts. In particular, red-green contrast, blue-yellow contrast, and black-white contrast. And these cells in our eyes could potentially be telling the brain, okay, you're not only seeing red, but you're seeing red not green, and blue not yellow, or something's dark not light. And this might seem almost redundant, but theoretically, by having these contrasting signals, you might be able to sort of adjust your color perception a little bit better and be a little bit clear in terms of the signals hitting your eyes and eventually your brains as to kind of what it is you're seeing in the environment. The catch is that if you do stare at something for a really long time and kind of burn out the message going to your brain might accidentally recalibrate a bit when these opponent process messages and cone messages just stop all of a sudden. Nowadays, we know that this idea of the opponent process theory is not only logical, but it seems to be something we can trace back to specific cells. In particular, when we look at our rods and cones in our eyes, what we see is they connect to very small cells called bipolar cells, and those very small cells called bipolar cells actually reach out to cells that collect information from multiple cell rods and cones and the bipolar cells connecting to them. Then these cells are called ganglion cells. Most researchers have concluded that these ganglion cells seem to be the source of this opponent process message that eventually reaches the brain. And it creates the weird after-image effects that we talked about and some weird lightness, darkness, contrast effects that we experience. But these researchers that look at these ganglion cells insist that more often than not, when our brain's not being overloaded for a long period of time, this message coming from the ganglion cells in conjunction with the message that's originating from the rods and cones gives people a slightly better perception of what's around them and gives us a nice clear image, or at least gets the brain create a nice clear image for the mind as we try to navigate in the color world around us. And if we're trying to tie this back to whether or not this is an ecological thing or a collectivist thing, or constructivist thing, understand that this also seems to be evidence for the ecological approach, because again, our brain is just taking a signal coming from the eyes, breaking it down into something that we can make better sense of. So is this all we need then? Is it just these things sending messages to the brain? Well, obviously there's probably more to it. The best way to explain how there's probably more to it is to actually bring us back to something that we started the class out with. For those of you that don't know, this is the image that we originally looked at for those 2 seconds at the beginning of the class. And I'm guessing that many of you did see people fishing in the church and boats and maybe the horse-drawn carriage and probably a couple animals. And in fact, you probably saw the vast majority of the things in this image. But you also probably missed some very peculiar things in it as well. You probably missed the fact that the person fishing in the front of the screen is either fishing with the longest rod in the history of the world, or there maybe is some perspective issues with that person. Same thing with the sign right above him, where you see it tucked behind some trees in the far distance somehow. If this image was a little bit clearer, you'd also see a person trying to get their pipe lit from somebody in a window. Unfortunately, that one seems to have been deleted. But there's other things that we can catch as well, like the fact that there's a church in a lake and the man shooting a gun into a bridge. And there is a gigantic swan, if you think about perspective, in numerous places that's oftentimes bigger than people, and the sheep, for some inexplicable reason, seem to be getting larger and larger as they move away to the point where the last sheep is huge if we think about 3D perspectives. There's all these issues, size issues, depth perspective issues, things being tucked in places they're not supposed to be, that we miss. And this leads you to say, well, okay, how did I miss this? Is there something more to, we say perception, or perception of, say, a situation? Well, this is more an understanding of a situation as a whole, not necessarily the stimuli around us, but it does lead us back to this question of, do we do more with colors? It's the basic elements, not of a situation, but of the stimuli that were being presented, then just break it down. Well, to answer this, I want you to look at the images to the right. I want you to ask yourself, which letters are most similar? My guess is that if you can see these things, you're saying in your mind, obviously A and D are very similar, and B and C are similar. But I promise you, when we connect those, if you want to do this, you can do it. If you've printed these out, fold a piece of paper together. What you will find is that B and D are actually the same color. You don't believe me if you're looking at this, but they are. The fact that you can't see this is a byproduct of an effect that we call color consistency, where we don't see colors necessarily based on exactly what they're sending to the back of our eyes. But instead, we see them based on what they're sending to the back of our eyes and our sort of course correction, small adjustments that we make in the decisions of what colors we're seeing based on the ambient light around us. So for the two images, you see A and B surrounded by red light or red colors. C and D are surrounded by a yellow block. Even though we're not realizing that we're making those calculations, we do factor those in, and we change our perceptions of what the color of box A and box B are and what the colors of box C and D are. And it gets us to, in these weird, odd situations, to misperceive which colors are identical there. And this is something that we find is going on all the time. We're oftentimes engaging in this color constancy sort of course correction. When we see somebody we're walking with transition from one room to another with different types of light, either brighter or maybe a different hue, we don't think that person has suddenly dramatically shifted what they're wearing or how they look. We just recognize that that light's changed, and we quickly kind of reconfigure our perception of the colors that we should be seeing based on that ambient light. This has led to some interesting debates, like the color of dresses or the colors of shoes or other things that you might have gotten involved with online. And if you're wondering why, a lot of this has to do with what cues we look at. The theory that explains how this effect occurs is something we call the Retinex theory of color vision. It surmises that color vision is very likely a byproduct of what our retina is sending to the brain, but it's also, in combination with that, a byproduct of what our mind is imparting upon that signal reaching the brain. It's us doing course corrections, alterations, to see things in the way we think is kind of the best way to see it. And mind you, this is oftentimes a beneficial thing to do. Just in case you didn't trust me, by the way, here you go. B and D. Now, how is this advantageous? Well, this is advantageous because it allows us to see things, say, with shadows that are altered as consistent. If I, say, asked you which blocks on these checkerboards were darker, the one circled on top or the one on the bottom, you wouldn't bat an eye if it was just a normal image that you were looking at. You would say, well, obviously, it's a much darker hue, the one on the top than the one on the bottom. But if I asked you as a painter which one you would have to paint darker if you were getting paints and trying to replicate this, well, you might pause for a second, but you probably still, because of how powerful this Retinex theory is, insist that the one on the top probably requires a slightly darker hue than the one in the middle. But in reality, if we connect those things, we see they're the exact same color. And this effect is pretty cool, because if I remove that connection, you will still, even though you just saw that they were the same color, see the top one is darker. I want you to remind yourself, as we're looking at this, that it doesn't mean that your brain is wrong more often than not. What it's doing is a 99.9% of the time accurate course correction as to what it is we're seeing. It's just, well, as a perceptual psychologist, we can create stimuli like this that tap into this technique we're using and kind of show us how things aren't always 100% accurate when we do it. And in fact, it's really tough to override when we start doing these things. Again, same color, I promise. So what explains this? Well, the only thing that could explain this effect, this Rett-NX theory, is this recognition that there is some validity or some usefulness to the constructivist approach that we talked about. Many people nowadays who look at color vision surmise that it's really not about if the ecological approach or the constructivist approach is right. It's instead how kind of each component, both the top-down and bottom-up processing, come together to allow us to see things like color. This is also true for a lot of other visual, perceptual, and all other types of sensation and perception experiences that we have. And to understand the kind of constructivist contributions that our mind are making to all the different perceptual experiences we have, numerous psychologists went off and started to try to kind of find rules that all of us seem to be using, like we talked about before with the color constancy approach. Nowadays, lots of these psychologists are called Gestaltist psychologists. They don't necessarily just study perception if you're looking at Gestalt psychology, but when we look at kind of the mind's impact on our experiences, and in this case, our basic processing of stimuli, Gestalt psychologists have found a lot of really interesting things. To explain kind of what they've concluded, they always like to quote something that comes from Gestalt psychology, and in particular the Gestaltist approach to perception. The statement is, the whole is greater than the sum of all of its parts. It suggests that, and even if we have an incomplete picture, our mind can kind of make stuff up or add things to give a complete image when something's not quite all there. Say, for example, if you looked at the phrase in the upper right-hand corner, immediately read the cat, you might assume that that's a pretty complete image. But if you look closer at the H and the A, you might recognize that those two letters are actually identical. It's just in one, since te isn't a word, you read the first one as an H, and since cht isn't a word, you read the second one as an A. Not even recognizing that you were doing that. This is the type of stuff that Gestaltists look at. The rules that we use, the things that we do to make the imperfect seem perfect in our minds. What a large number of them did in the early years, in the kind of mid to early 1900s, was come up with rules, laws, and principles that our mind was using to make better sense of the world around us. You see, some of the rules that we came up with, Gestaltists came up with, is pictured in the lower right-hand corner. I see the law of proximity, the law of similarity, the law of continuity and connectedness that suggests that we don't just see those images as they are, but as kind of morphed things based on some of the things our mind is automatically doing to the stimuli. The law of proximity suggests we don't see 6 random lines pointing upward, we see 3 pairs of lines. The law of similarity suggests we don't just see 9 random shapes, we see 3 columns of shapes, a column of triangles, a column of circles, and another column of triangles. My favorite is the law of continuity that suggests we don't see a bunch of moguls up and down, up and down, up and down. Usually when we look at that, we see a line across with a squiggly line transcending it over and over again. These basic laws and principles came in a wide variety of forms. If you take a cognitive psych class, you might learn about some of them. If you take a sensation and perception class, you'll definitely learn about some of them, and each of them have their utility, It's probably important to note that we even have some current psychologists looking at new things that can be added to the list. One of them is a gentleman named Steve Palmer, who spent many years at Berkeley looking at these ideas. But for the most part, these rules have their limits, but they can give us a better kind of holistic picture of perception. When we use them in combination, we can recognize how, again, we can take basic stuff that's very imperfect and in our minds make it seem pretty darn complete. My favorite example of this is this image that you see in front of you. Now, for those of you that have had an intro class before, or maybe just stumbled across this before, you might see the image in front of you is crystal clear. You might know exactly what's there. You might see some of the things in the background. You might understand exactly what you're looking at. And in fact, it's almost impossible not to see it if you've encountered this before. But if you've never had an intro class, you might see just a weird collection of random blobs on a sheet of paper. This might be something you won't ever quite break down in the next minute or two that we're going through it. And I promise, if you spend a bit more time, maybe pause me or go back to this eventually, if you look at this long enough, your eyes start to take in the picture and you start to recognize certain things like little black round things that sort of look like eyes and things that sort of look like ears. Eventually, your mind, your eyes, will start to see an image emerge. And as you start to add stuff, the image gets clearer and clearer and clearer until even though you know it's not a complete picture and there's little spots that are missing, it looks pretty darn complete and it looks like an obvious thing that your brain can't imagine how it missed. That's the power of the Gestaltist approach, the top-down processing. We can take something that is extremely incomplete and make it into something that's useful, make it into something we can understand. And this is true, again, not only for color perception, but all types of not only visual perception, but perception of stimuli for all of our different senses. Once people got on this track, trying to understand visual perception in this way, they started to really tinker with things that could sort of blow our minds, giving us a better sense of what we do in terms of memory and attention and focus to kind of come up with weird tricks that we can play on us. One of my favorite examples is when researchers recognize how we tend to focus on things even in two dimensions as if they were three-dimensional shapes. So if you see the picture on the left, you'll notice that you have two men arguing about how there's 4 blocks in front of them or 3, and depending upon which side you're looking at, both seem to be right. It takes a little while to break down that it's actually just a weird picture that kind of forces our brains to try to see this as something that's logical, and in reality, it's extremely flawed. The next picture over, for those of you wondering, is either, for those of you that are looking at it for the first time, an image of an old woman or a young woman looking away. Depends upon what you focused on first. And I promise, both images are there. But what Gestaltists and other perceptual psychologists have found is that once you dedicate yourself to one image, it's really tough to see the other. But to give yourself time, maybe pause me, you'll see both eventually, highlighting how important our original experience and where our attention is drawn first is when it comes to visual perception. Another thing which is really cool is how microscopic changes in our attention can shift what it is we're seeing. If you look at the picture to the right of the two different women, you'll see it looks like a basic cube. But if you look long enough, you'll see that the cube, either forcing down or facing up, suddenly switches in its direction. It might suddenly go down or suddenly go up, depending upon where your focus is at the time. You might not even recognize what you're doing to see it bend in those different ways. If you get really good at it, though, you can sort of develop the skills to make it go up and down at your will. But all of this kind of highlights how perception is not just the breakdown of stimuli. There's input that we have on it that shapes what it is we're seeing, and also sometimes shapes what it is we miss. If you look at the image on the far right, you'll see first, if you look at the vase itself, a weird sort of misshapen vase, one that maybe you might think needs to go back into the kiln because things are extremely off. But if you look at its image on the back, or that's image, but its shadow that's reflected onto the wall behind it, you might notice something if you look closely. And that's the two faces that are looking at each other in that vase. It's almost impossible to see them when you look at the vase itself, but when you just shift your attention, you can recognize that there's more to that vase than you had originally thought. This leads us to a really important point. Not only can these things highlight how interesting perception is and how important our mind is in it, but they also highlight how, if we come up with cool stuff, it can really draw in our attention and give us this kind of aha experience that's almost enjoyable and gives us a better understanding of how much our mind really does play with us sometimes. And this is the same insight that lots of cognitive psychologists had. They recognize that we can look at these things to better understand perception, or we could develop things after we understand perception to really kind of embrace how impactful our mind is on our everyday experiences. And this led people to come up with lots of what we call optical illusions. One of my favorite optical illusions is the one you see pictured here, something called the Mueller-Lyer illusion. It might seem simple to us now, but at the time when it was introduced, it was a breakthrough. It gave us this perception, or this, I guess, ability to identify that our perception of size was highly dependent on our perception of depth. If you look at these two lines, the ones in the middle on these two different shapes, you might, when looking at it, think that one of the lines is slightly longer than the other. In particular, the one on the right seems to be slightly longer than the one on the left. But I promise you, if we remove the lines connecting to those two vertical lines, what you'll see is that they are the exact same size. And this specific effect is very similar to something that we call the Pons illusion, where we start to look at two lengths of lines that are different heights and perceive them as different, not because of the kind of expansion or shrinking of things, but because of the introduction of something that we call a horizon point. These examples of the Pons illusion, one on the right being the original one, ask people to judge the length of two lines that seem slightly off but are exactly the same. I do think that the vanishing point in the one on the right is not quite as effective as the one on the left, but the one on the right is the original Pons illusion, so I like to include that. But if you're looking for kind of my favorite example of things that people just cannot get their mind around, it's the one on the left. You see the two highlighted vertical lines, and I'm guessing most of you, when looking at them, are very insistent that even though you know they're supposed to be the same, the one on the left has to be significantly smaller than the one on the right. But if you're watching this on your computer screen, you can put your finger up to it, a piece of paper up to it, and measure the two lines. And you will find that despite what your brain is screaming at you, those two lines are exactly the same size. If you printed out the slides, check it out. They're exactly the same size. But because of vanishing points, because of how things are designed around it, our brains almost refuse to identify that. Again, highlighting not only the impact that our expectations have on things, but how cool it is once we understand these things and what we can come up with when we do have a good grasp on these specific types of effects. And in fact, in the Bay Area and other areas as well, researchers have taken these effects to extraordinary levels. One of the best places you could possibly go to really highlight how much things like size perception and depth perception really do depend on our mental input are places that have these things called Ames rooms. In fact, we have a place in the Bay Area called the Exploratorium that I'm hoping you can someday visit that has this Ames room set up. So you go in and you look through a hole and you look at two people that look like they're extremely different sizes. And if you're lucky enough, you'll have those people that you're looking at switch positions and see that they're actually, well, the same size. They just look big or small based on where they are in these rooms. When you go into the Ames room after, you'll see that this particular room, even though it looks fairly normal from where you're looking at, is one giant optical illusion, taking advantage of the many things that we've learned about how depth perception and size perception actually works. And again, this is just one small aspect of perception, and it's just visual perception, not all of our perceptual skills. When you combine these things together, well, you find a lot to study and a lot of really cool effects that you can come up with. And this brings us to sort of a close on the topic. If we're looking to sort of conclude some of the questions that we had earlier, who's right, constructivist or ecological psychologist, we should understand that most cognitive psychologists nowadays don't really want to give one group credit for being right or wrong. What most cognitive psychologists do nowadays is look at how something like perception works from both angles. We now again call it the top-down or bottom-up processing approach, and we can look at this on either the basic perceptual level of stimuli or our basic perception of, say, a situation. And when we study these things, how this information from our sensory organs gets to the mind for all of our different senses, we got a lot to study. It's also important to remind you that this is just one area of cognitive psychology that people are trying to tackle. In our next class, we're going to be looking at another topic within cognitive psychology that people study. So if you can, make sure you're well studied, ready to go, and we'll tackle that at the time. But for now, we're out of time. So have a great evening, or a great day, depending upon when you watch this, and I hope to see you soon. Take care.